All right, these are your notes for this week. First of all, we are going to. Normally, I have a little example lab or demo that we use. So, normally, I use this little guy, and I think I've pulled this out before for some of you. It's basically a broomstick with a weight attached at the end. And I'm going to ask you to make your own. So, basically, you can get a ruler, a meter stick, or just any kind of stick, and tape like a can of soup to it. All right. It doesn't have to be anything super heavy. Just duct tape a can of soup to it, or however you can get a can of soup attached to it. And we're going to do some experiments. So the first thing I want you to do is, once you get that thing taped to the end, so if you haven't done that yet, please try to figure out a way to do this, or you can just kind of imagine it along with me. If you tape the soup here, so we're going to put the soup, this is going to be the soup can, and you're going to attach your hand onto the other side. Now, I cannot draw, so I'm just representing your hand with that arrow, okay? So your hand's going to go there, and you're going to try to move the soup. And then what you're going to do is you're going to flip it over, and you're going to put the soup right beside your hand. So in step 2, you're going to put the soup and your hand right next to each other, and you're going to try to move it again. What you should notice is that when the soup is farther away, it's harder to rotate. So this version right here is harder to rotate. And then we also have, I'd also like you to kind of create a seesaw. So with the same soup and stick, create a seesaw. Just get something that you can like use to pivot your stick. Could be another stick, could be another can of stuff or whatever. Just something that you can use. And what I want you to do is to move that pivot point back and forth and push down on this side and see where is it easiest to lift the object. So when is it easiest to lift the object? And what you should notice is that it's easiest to lift the object when you're pushing farther away from the pivot point. So like if you put the pivot point at point 1 or 2, this one should be harder and this one should be easier if the soup is right here. All right. So again, you don't have to use soup, but I'm just saying. So those are the activities I'd kind of like you to do. And so what do we notice in the cases that make it more difficult to move the object? Basically, what you should be noticing is the farther the object is from your rotation point, the harder it is to turn. So basically, if you look at our first example, when you have that soup farther away from your hand, it's more difficult to rotate. And whenever you have the pivot point whenever you have the soup closer to the pivot point, it becomes easier to rotate. So the farther the object, in this case we're going to be referring to the soup, the farther the soup is from your rotation point, the harder it is to rotate. And the closer that soup is to your rotation point, so for example here there's not much difference between it, and here it's much closer. The closer it is, the easier it is to rotate. And the reason for why that is torque. We're going to talk more about this in a little bit. Would increasing the mass make these tasks harder? And the answer is yes. If you increase the mass, it would make these tasks harder. What other factor seems to make a difference? You should notice that it's the distance from rotation. So if you bring that object that you're trying to rotate closer to the axis of rotation, it becomes easier to rotate it. Also notice on the seesaw, if you move the force that you're applying farther from the axis of rotation, it also makes it easier. And again, this has to do with torque. So notice on this one, the farther you are away, the farther you're pushing away, the easier it is to get the soup to rotate. And so we're going to talk more about these in a second. But just play around with that. That's a fairly simple example for you to set up. It shouldn't take too long. Most everybody should be able to find something to do this with. Again, it could be a stick, could be a meter stick, a ruler, an old board you got outside, something. And if you can't find one, then just kind of bear with me, because it's one of those things that helps a lot to get your mind around it. But I tried to give some little examples here. But again, nothing can really replace you actually doing it. All right, so there's a lot to this one. This first slide, whenever you look at it, it's going to scare you, and it should. It's a little bit overwhelming. So rotational motion is what we are starting now. It is essentially all the stuff we've done so far this year, but now we need to talk about what it means if you're rotating. So essentially, what you should notice first is that we've got linear motion and rotational motion, and every one of them has an equivalent, all right? So whatever we dealt with in linear motion, there's an equivalent in rotational motion. So for example, in linear motion, we had x, or distance. In angular, we're going to have theta. That's going to be the angular position. In linear, we had velocity. We're going to have angular velocity, and this is the Greek letter omega. Acceleration, we had acceleration, and we also have angular acceleration, and that's a Greek letter alpha. When we did our formulas, we had x is equal to vt, or v is equal to, you might have wrote it as v is equal to x over t. Same thing applies here. Omega is equal to theta over t, and they've just written it slightly differently. All of these equations are the same. You should recognize them. They're just subbing out omega and alpha for velocity and acceleration. Mass. So mass has an equivalent. It's going to be called the moment of inertia, and we'll talk more about that in a little bit. Newton's second law is F equals ma. The thing for torque is equal to I alpha. So instead of F equals ma, we have torque is equal to I alpha. And again, mass is the same thing as I. Alpha is the same thing as acceleration. Momentum is mass times velocity. Angular momentum is moment of inertia times velocity, times angular velocity. Work, force times distance. Work that in rotation is torque times the angle, or the angular position. Kinetic energy, 1/2 mv squared. Kinetic energy, 1/2 I omega squared. Power, force times velocity. Torque times omega. So all these things have equivalencies. It's going to be very difficult for you to remember them all off the top of your head, so you might just want to screenshot this right here and add it in to your notes, because it'll be helpful to refer back to it. Now, the next thing here, I do not want you to freak out and think you have to memorize all this stuff, because you most certainly do not. But these are all the different ways you can do moments of inertia. Moments of inertia describe basically how difficult it is to get the object to begin to rotate. Just like mass is how difficult it is, can be described as how difficult it is to get it to move. The more massive you are, the harder it is to get you to move. The less massive, the easier it is. The lower your moment of inertia, the easier it is to get you to move. The higher your moment of inertia, the harder it is to get you to move. And in this case, when we're talking about movement, we're talking about rotation. The key for us, I think, is going to be to know that the moment of inertia, I, is, if not equal to, at least related to mr squared. And let's investigate what this means. First of all, this is the mass, and this is the radius. Whoops. This is the radius from the rotation point. And so one of the reasons that we had earlier, we were doing, when we had the soup can, when we were trying to, we had our hand here and the soup here, we had a larger I. So I was much larger because we had a larger R. All right, we were trying to rotate it from this point right here, which meant that we had a big R, which meant that it was harder to move. It was basically making it more difficult to move. The analogy would be is we kind of made it have more mass if we're talking about linear motion. When we instead put our hands and the soup right next to each other, we shrunk the moment of inertia and made it easier to move. So that's one way to look at it. But basically, you need to know that if you increase the mass, it becomes harder to rotate. And if you increase the radius, it becomes harder to rotate. And also, it's a square factor. So it's the farther out you put it, the more difficult it is to get it to move by a square factor. So, for example, if I was doing the soup example, if I had the soup here versus here, let's say that this is L, and this is L over 2. Well, I'm doubling that distance, and so what I would be doing is actually making it 4 times more difficult to move. All right? And again, the thing that I think you need to keep in mind most is this right here. The relationship, the moment of inertia is related to mr squared. There's all kinds of different things you can look through here if you want to. There's all kinds of different ones you can look at, but they all have something to do with mr squared. Okay. Moving on, we have torque. So specifically, torque is a force applied a distance away from a center of rotation to rotate the object. So torque is going to be in Newton meters. The symbol for a torque is the Greek letter tau. So this is the Greek letter tau. It stands for torque, and it's a force applied at a radius. It is important to note that the torque for the torque to work, the force has to be perpendicular to the radius. So if you look at the example on the right there, if you have a force that's at an angle, you have one component that's going to be perpendicular and one component that's going to be parallel. It's the force that's perpendicular that you're going to need to multiply by the radius. By the way, the radius on this one would be this right there. Okay, that would be your radius, whatever that distance is. If the force is not perpendicular, it does not apply a torque. Okay, so in that little chart next to it, you're looking at which one provides more torque. So in the first example, you're pulling up at an angle. It doesn't apply as much torque if you apply that same force straight up, because now let's call this 1 and this 2. In 2, all of your force is directed the same way. It doesn't get split into components, and so you're applying more torque. And then in number 3, we're applying even more torque because we've made that radius even larger by applying a pipe to the end of the wrench. By the way, if you have a bolt that's stuck, classic example is if you get a bolt stuck at the bottom of a lawnmower, one easy way to get it off, or one easy way to help you get it off, is to attach a long pipe to the end of your wrench, and it'll help give you enough leverage, give you enough torque to pull it off. So importantly, the force and the lever arm need to be at right angles. This is very, very critical. If they are not, you need to use the component of the force that is at the right angle to the lever arm. Okay, so what would happen if you tried to have a force acting at the axis of rotation? Well, let me go back to these guys again. So I'm going to zoom in, and maybe I'm going to zoom in. Okay. So we are going to look at these guys. If I wanted to have the force acting right here, so let's say that I applied, I don't know how, but let's say that I applied a force right here, a big old force. All right. Would it actually provide a torque? Could it twist the bolt? And the answer is no, because a torque has to have a force and a radius. It does not matter how big that force is. If the radius is 0, then the torque is still 0. So if you apply a force at the radius, at the axis of rotation, the radius is 0, and therefore you have no torque, and it will not turn. All right, so final page, let us look through a few things. So now, if you'll remember, when we talked about force, we said that Newton's second law, F equals ma. So if you imagine that equivalent, what this means is that you will sum up all the torques acting on an object, and that will be equal to I alpha. And again, I is going to be some relationship of mr squared. But basically, the more torque you apply, the bigger your acceleration is, the bigger your angular acceleration is. If your net torque is equal to 0, you will not be rotating. If you need to make sure that the object is not rotating, you need to make sure your counterclockwise torques are equal to your clockwise torques, and that will ensure equilibrium, all right, meaning they will not move. Another way to say this is that if you apply a net torque to an object, it will cause it to rotate. All right. One final note on torque is that rather than saying left or right or up or down, we do clockwise and counterclockwise. So CCW is counterclockwise, CW is clockwise. All right, what happens if you have two torques on opposite sides of the axis of rotation that are of equal value to each other? So for example, what happens if I take a balance beam and I put a 50 Newton force here and a 50 Newton force here, and then there's the same R away from the center? Well, in that case, this one is applying a counterclockwise torque. Basically, it's wanting it to rotate this way. This one's applying a clockwise torque, wanting it to rotate this way. If they're the same, they're equal to each other, which means that the net torque is going to be equal to 0, which means that it will not rotate. All right, so let's take a look at some of these questions. I pulled some questions just to ask you. If a doorknob were placed in the center of a door rather than at the edge, how much more force would be needed to produce the same torque? So basically, we would have torque is equal to force times the radius of the door. So like, basically what I'm saying is that this is the original. The original torque would be force times the radius. So if we want to produce the same torque, and we are putting it in the middle of the door, notice that we would have to half the radius, so we would have to double the force. So we'd have to have double the force because you're halving the radius. All right, if you cannot exert enough torque on a stubborn bolt, would more torque be applied if you fasten the length of rope shown above? The answer is no, because you're applying this force here, but the radius hasn't changed. So as long as you're applying the same force you would have by just grabbing the wrench, then you're not really doing anything different, because F times R is still the same, because that force is still acting at a distance R from the radius. What you'd really need to do is to add some kind of pipe here and then attach the rope, and then you would be adding some more torque. Okay, 14. All right, each of the forces shown here acts upon the block with a strength of 100 newtons. The center of rotation and lines of action are shown for each scenario. Which of the four scenarios show the block in force equilibrium? Okay, force equilibrium means that the forces are balanced. So which of these forces are balanced? And the answer would be 1, 2, and 4, because all three of those have 100 this way, 100 this way, 100 this way, 100 this way. So basically what that means is that there is not going to be no linear acceleration for these objects. Okay? But what about which of these four scenarios show the block in rotational equilibrium? Well, rotational equilibrium means there's no torque. So there's no torque. So which of these has no torque? And the answer there would be 1, 3, and 4. Now, why does number 3 just has one force acting on it? So why doesn't it have a torque? Well, the answer is the axis of rotation is right here, and so the force times the radius, the distance from the axis of rotation, would be force times 0, because there is no distance from the axis of rotation. The same thing is true on number 1. There's two forces acting on it, but the radius for both of them is 0, so the torque is 0, meaning that it will not spin. And then finally, number 4 over here has two forces acting on it, but one is going to be pushing it this way, and one is going to be pushing it this way. And since they both have the same force and the same radius, they provide no torque, no net torque, because they cancel each other out. The only one that would be spinning would be 2, because it would have notice that this one would be pushing it this way, and this one would be pushing it this way. Those are the same direction. They're both pushing it clockwise. And so even though they're on different sides, they're both pushing it clockwise, and so you would have a net torque, and it would begin to accelerate. All right, which is easier for prying open the cover of a can of paint, a screwdriver with a thick handle or a long handle? Well, the long handle would be more useful, because you could, wedge it in, and then the longer the handle is, the bigger your R is and the easier it is to apply a push that would provide enough torque to lift it. But which would be more handy in turning a stubborn screw? The stubborn screw, you'd be better off with a thick handle. And basically the reason for that is as opposed to this one, it wouldn't do you any good to have a longer handle. You would want a thicker handle so that you'd have a bigger radius about which you were twisting. Okay. Number 3, in which direction should a force be applied to produce maximum torque? And the answer is it's got to be perpendicular. Goodness gracious. Perpendicular, there you go, to the radius. So the force has got to be perpendicular to the radius. Number 4, you cannot stand with your heels and back to the wall and successfully lean over and touch your toes. Please try this. It's fun. Very, very much the case. So stand with your heels up against the wall, try to bend over and touch your toes. Would either stronger legs or feet help you do this? The answer is no. And the reason is because you're basically, whenever you bend over to touch your toes, your butt goes backwards to try to help balance you out, basically to provide a torque in the opposite direction from your upper body. And without being able to move your butt backwards, there's a positive torque pulling you forwards and you fall over. If you are able to bend over without, if you are able to not have the wall behind you, then basically your butt provides a torque in the opposite direction from your upper body, and you are able to balance out. All right, number 5, if you walk along the top of the fence, why does holding your arms out help you balance? Basically, holding your arms out increases your I. It increases your moment of inertia. Because remember, it's related to mr squared. So if you hold your arms in, then the R is smaller than if you hold your arms out. And I'm greatly exaggerating the arms. You might also see people who, for instance, are doing things like tightrope walking, like this person. And whenever you see these people doing the tightrope walking, basically they have these big sticks or rods or something that go out like this, and those are basically designed to increase their I so that it makes this R value go up. What that means then is that whenever you're doing torque equals I alpha, you have a much bigger I, so you need a much bigger torque to get yourself to angularly accelerate, to start moving around in a circle. And so having these things basically makes it harder to start spinning in a circle. You can kind of get this if you try to balance your soup taped stick. If you try to balance it with the soup away from your hand, it's actually easier to balance it than if the soup is right next to your hand. If you try to balance it on one finger, try to balance it on one finger with it away and next to you. So try balancing it like this. This is your finger right here. There you go. That's a finger. I don't know why I'm trying to draw. That's a finger. So try balancing it like that, and then try balancing it like this. There's your finger again. All right. And weirdly, this one's easier to balance because it's got a higher moment of inertia, which means it's more difficult to get it to spin. This one right here always wants to flop over real fast and real easily. All right. So hopefully that was helpful to you, and go deer.